For over a century, there was one thing about our galaxy's future that astronomers agreed on. The Andromeda Galaxy, our nearest large neighbor, 2.5 million light-years away, was coming toward us. Not drifting, not wandering. Moving with direction and momentum toward the Milky Way at roughly 110 kilometers per second. The math was considered settled. The collision between our galaxy and Andromeda was not a question of whether. It was a question of when. In 2012, NASA's Hubble Space Telescope provided what many in the field called the definitive confirmation. The data showed Andromeda's sideways motion was negligible. That meant a head-on encounter was essentially certain. The timeline, approximately 4.5 billion years. This was not a fringe prediction. It was reproduced in textbooks, presented at conferences, visualized in NASA simulations, and repeated in every serious documentary about the fate of our galaxy. The Milky Way and Andromeda collision was described, with confidence, as inevitable. In June 2025, a team of astronomers from the University of Helsinki, Durham University, and the University of Toulouse published a paper in the journal Nature Astronomy. The title was measured, as scientific titles tend to be. It contained 5 words that quietly dismantled what had been, for over a decade, a cornerstone of our understanding of galactic dynamics. Those 5 words: no certainty of a collision. For the next hour, this documentary will examine every layer of that conclusion. What the new data shows, why it changes the previous models, what a second completely independent anomaly discovered in the same year adds to the picture, and what both findings together reveal about how much we thought we knew about the future of the galaxies we live in. This is a full documentary investigation. We are not going to skim the surface. We are going to follow the evidence wherever it leads, and be honest about what it does and does not tell us. Let's begin. The story of how we came to believe in the Milky Way-Andromeda collision is not a story of bad science. It's actually a story of science working exactly the way it is supposed to. Building evidence carefully, refining measurements over time, and arriving at conclusions that the available data supported. The problem is not what was done. The problem is what was left out. Let's go back to the beginning. As far back as 1912, the astronomer Vesto Slipher, working at the Lowell Observatory in Arizona, measured something unusual about the Andromeda Galaxy, which, at the time, was still thought by many to be a nebula within our own galaxy, not a separate galaxy at all. Slipher was analyzing its spectral signature, the way its light shifted toward the blue end of the spectrum. Blue shift means an object is moving toward you. And Andromeda, Slipher found, was moving toward us at a remarkable speed. That discovery sat in the scientific literature for decades. It was not until the 20th century had further advanced, until Edwin Hubble had confirmed that the Andromeda Galaxy was indeed a galaxy, a vast, separate island of stars more than 2 million light-years away, that the full significance of that blue shift was appreciated. If the Andromeda Galaxy was that far away and moving toward us that fast, the arithmetic was straightforward. If you know how far apart two objects are, and you know their velocities, you can calculate when they will meet. Astronomers did, and the numbers suggested that in several billion years, something very large was headed our way. By the early 2000s, this had become standard cosmological knowledge. But the precision of that prediction depended on something specific. Knowing not just how fast Andromeda was coming toward us, but whether it was coming directly or at an angle. That second measurement, in what scientists call the transverse velocity, the sideways motion, was extraordinarily difficult to make. The Andromeda Galaxy is so far away and its sideways drift so slow relative to its distance that measuring it required an instrument sensitive beyond anything that existed until relatively recently. If you like the kind of deep dive this channel does, the like button helps this reach more people who'd want to spend an hour on this. That instrument arrived in the form of the Hubble Space Telescope. Over years of observation, patient, meticulous, tracking the positions of individual stars in Andromeda across multiple observing campaigns. Astronomers accumulated enough data to attempt that transverse velocity measurement. And in 2012, the team led by Roland van der Merel at the Space Telescope Science Institute published their findings. The sideways motion of Andromeda was, to all intents and purposes, negligible. Almost zero. The implications were immediate. If Andromeda had almost no sideways motion, it was not coming at a glancing angle. It was coming almost directly toward us. The collision would not be a near miss. It would be a merger. The 2012 paper stated with confidence that the Milky Way and Andromeda would collide in roughly 4 billion years, and that this collision would eventually result in the two spiral galaxies merging into a single, larger elliptical galaxy, a structure some astronomers took to calling Milkomeda or Lactomeda. The collision was, the paper concluded, essentially inevitable. This conclusion was reproduced. It was cited. It was used as the basis for follow-up papers calculating where our solar system might end up after the merger, what the night sky would look like in 3 billion years, and how the merger would affect star formation rates. An entire branch of research took that 2012 certainty as its foundation. And here's the thing that is worth holding on to as we go further into this investigation. The 2012 team was not wrong to publish what they published. They had the best data available. They used rigorous methods. Their conclusions followed from their measurements. This was not a failure of science. What it was, as we are about to examine, was a picture with part of the frame cut off. The measurements captured what they were designed to capture. What they could not yet fully account for, what no existing data set at the time had the precision to measure, were two factors that would, a decade later, change the answer. The first factor involved other members of our local group, the collection of several dozen galaxies gravitationally bound together in our cosmic neighborhood. Specifically, it involved a galaxy you may know by name, but may not have thought of as a significant player in this story: the Large Magellanic Cloud. The second factor was something built into the 2012 analysis that its authors openly acknowledged at the time, but that would prove more consequential than anyone anticipated: the uncertainties. Not errors, uncertainties. The gaps in precision that are inherent in any measurement, particularly one attempting to track the sideways drift of a galaxy 2.5 million light-years away, from a vantage point inside a galaxy that is itself moving. We will examine both in detail. But first, it is worth understanding exactly what the new analysis in 2025 set out to do, and what it found when it actually did it. The 2025 team did not simply update the 2012 numbers. They built an entirely new framework for the question. They ran 100,000 separate simulations of the local group's evolution over the next 10 billion years. Not one simulation, not 10, 100,000. And they factored in not just the two largest players, the Milky Way and Andromeda, but also two of the most massive satellite galaxies in the neighborhood, the Triangulum Galaxy, which orbits Andromeda, and the Large Magellanic Cloud, which orbits us. That last addition, as we will see, is the one that changes everything. To understand what the 2025 paper found, it helps to understand precisely what was being measured, and precisely why that measurement was so difficult that even world-class instruments, run by world-class teams, could only capture part of the picture. The Andromeda Galaxy is moving toward us. That much is not in dispute. It was not in dispute in 1912. It is not in dispute now. What astronomers have been trying to nail down with increasing precision for over a century is the exact nature of that motion, the full, three-dimensional trajectory. Think of it this way: if you are standing on a train platform and a train is approaching, you can hear that it is getting louder, which tells you something about its speed towards you. But whether it is coming directly at the platform, or whether it will pass slightly to your left or right, that requires a different kind of observation. You need to see its lateral position changing over time. That lateral measurement, the transverse velocity, the sideways component of Andromeda's motion, is exactly what was difficult to obtain. Andromeda is 2.5 million light-years away. Its sideways drift, relative to that distance, is almost imperceptibly slow. Detecting it at all requires measuring the positions of individual stars in Andromeda across years or decades of observation, with enough precision to detect changes in positions smaller than a millionth of a degree. The Hubble measurements accomplished this. They were remarkable in what they achieved. But what they captured were the positions and movements of stars under specific observing conditions, over a specific time window, measured against specific reference objects. Any uncertainty in those reference points, any imprecision in the baseline measurements of the galaxy's masses, any factor not yet included in the model, propagated forward through the entire calculation. When the 2012 team ran their analysis and found that the transverse velocity was essentially zero, that finding depended on a set of measurements that were the best available at the time. What it could not fully incorporate was the gravitational influence of every significant object in the local group. The 2025 team began with a question that sounds deceptively simple. What happens to the Milky Way Andromeda trajectory when you include every significant gravitational player in the neighborhood? Not just the Milky Way and Andromeda, all four of the most massive local group members. And what happens when you take every measurement uncertainty, every error bar, every range in the mass estimates, every margin in the velocity data, and run not one simulation but 100,000, sampling across all of them? What they found was this. The models said the collision was certain within 5 billion years. The probability, in the 2012 framework, approaching 100%. The probability in the 2025 framework, running 100,000 simulations with updated data from both Hubble and the Gaia Space Telescope, 2%. Not slightly less likely than we thought. Not a revised timeline. The probability of a direct collision within the next 5 billion years, the specific collision that has been described as inevitable in textbooks and documentaries for over a decade, is, according to the most comprehensive analysis ever performed on this question, approximately 2%. That number requires some unpacking, because it is easy to read it as saying the collision won't happen. That is not what it says. The paper's authors were careful on this point. What they found was that in roughly half of their 100,000 simulations, the Milky Way and Andromeda do eventually merge, but on a much longer timeline, somewhere between 8 and 10 billion years, not 4 to 5. And in most of the remaining simulations, the two galaxies pass each other at significant distance and continue on separate paths, their interaction limited to gravitational tidal forces rather than a full merger. Only 2% of simulations, 2 out of every 100, showed the specific head-on collision at the 5 billion year mark that had been described as essentially certain since 2012. The lead author of the paper, Dr. Till Sawala of the University of Helsinki, was explicit about what this finding did and did not mean. Even using the latest and most precise observational data available, he said, the future of the local group of several dozen galaxies is uncertain. The study's co-author, Professor Carlos Frank of Durham University, put it plainly. Until now, we thought this was the fate that awaited our Milky Way galaxy. We now know that there is a very good chance that we may avoid that scary destiny. These are not fringe voices. Frank is one of the architects of the cold, dark matter cosmological model, the standard framework used to understand galaxy formation and evolution. When he describes a result as fundamentally revising our understanding, he is speaking from a position of deep investment in the models that are being revised. There is a detail buried in the paper that deserves attention, because it points directly to why the revision was so significant. The models said, collision certain. The data said, check again. They checked. The certainty was gone. How does a prediction that confident get that wrong? not through error, through incompleteness. The 2012 analysis treated the Milky Way Andromeda system as essentially a two-body problem. Two massive galaxies, gravitationally attracted, moving toward each other on a calculable trajectory. That model was not wrong. It was simply missing variables that could not be measured with the precision that the question required. There is something scientifically uncomfortable about that. The variables that turned out to matter were not small. The Large Magellanic Cloud, the galaxy whose gravitational influence proved to be, as we are about to examine, a decisive factor in the outcome, is the most massive satellite galaxy in the Milky Way's orbit. Its mass is roughly 15% of the Milky Way's. It is not a trace element in the calculation. It is a significant fraction of the total system. And yet its gravitational effect on the Milky Way Andromeda trajectory had not been fully incorporated into the prior prediction. There is one additional element in the 2025 paper that the popular coverage of this story largely passed over. The paper notes explicitly that new data from the Gaia Space Telescope, data expected to arrive in the summer of 2026, will provide more precise measurements of Andromeda's transverse motion. The authors stated that those measurements will likely refine and possibly further revise their current 50-50 probability estimate, which means the question is not only open, it is actively being answered. New data is coming, and when it arrives, what we've examined in these first 20 minutes of this documentary will either be confirmed, modified, or overturned again. There is a second data set in this story, a second independent set of measurements that, when placed alongside the 2025 paper, produces a contradiction that Chapter 3 will examine in detail. It involves the satellite galaxies of Andromeda itself, and what it shows is stranger than what we've discussed so far. At the start of this documentary, the question was simple: is the Milky Way Andromeda collision actually going to happen? The first two chapters have examined how that certainty was built, and how one 2025 paper revised it from near certainty to a coin flip. That revision is significant on its own, but it explains only part of what is anomalous about the Andromeda system. Because there is a second, completely independent finding from 2025, published in the same journal 3 months earlier, that concerns Andromeda's relationship to its own satellite galaxies. And that finding, explained in full, is what this documentary is really about. The two anomalies are connected, and together, they suggest that our models of how this specific corner of the universe behaves are wrong in more than one way simultaneously. If you've stayed with this investigation so far, the next chapter is where the full picture comes into focus. Let's step back from the collision question for a moment and look at the data more carefully. Because there is a detail in the 2025 paper that has not received the attention it deserves, and it concerns the very tools that were used to revise the prediction. The 2025 Sawala team used data from two sources: the NASA ESA Hubble Space Telescope and the European Space Agency's Gaia telescope. These are not the same instruments. They do not measure the same things. They were built at different times for somewhat different purposes, and they observe from the same basic location, Earth orbit, but with different capabilities and different observational records. Hubble was designed with extraordinary light-gathering capability and precision imaging, used to track the positional shifts of individual stars over time. Gaia was designed specifically for astrometry, the precise measurement of stellar positions and motions, at a scale and accuracy that had never been attempted before. Gaia's data catalog, released in stages between 2018 and its most recent release, has transformed what is measurable in our cosmic neighborhood. When the 2025 team combined Hubble's long baseline observations with Gaia's precision astrometry, they got a more complete picture of Andromeda's three-dimensional motion than had ever previously been available. And that more complete picture was what drove the revision. Here is what the 2012 analysis could and could not measure. The component of Andromeda's motion that 2012 Hubble data captured most accurately was its motion along the line of sight. The radial velocity, the component coming directly toward us. That measurement was robust. Andromeda is, unambiguously, moving toward the Milky Way. That has not changed. What was uncertain, and what remained uncertain even after 2012, was the transverse component, the sideways motion. And the 2025 team found, when they incorporated the most recent Gaia data and accounted explicitly for the observational uncertainties in the reference frame, that the transverse velocity has a much wider range of plausible values than the 2012 analysis suggested. This is the mechanism of the revision, not a discovery that the 2012 team made an error, a discovery that the uncertainty range, the range of values that the data is genuinely consistent with, is wider than the 2012 framework captured. And when you run 100,000 simulation sampling across that wider range, the outcome distribution changes dramatically. But there is something that makes this more than a straightforward measurement refinement. Because when the 2025 team looked at the full probability distribution across their simulations, they found a specific pattern in the outcomes. In the simulations where the Milky Way and Andromeda did not merge within the 5 billion year window, the majority of simulations, the two galaxies did not simply fly apart. They came close. In many cases, separated by less than 500,000 light-years, roughly 5 times the diameter of the Milky Way. Close enough for gravitational tidal forces to distort both galaxies significantly. In these scenarios, the Milky Way and Andromeda survive as distinct galaxies, but neither of them survives unchanged. Two possible outcomes. One is a full merger, the collision that has been described for decades, in which both galaxies cease to exist as spirals and form a single large elliptical system. The other is a close flyby, in which both galaxies are deformed, stripped of outer material, possibly spun into new shapes, but remain structurally intact. The 2025 paper put the probability at approximately 50-50 for whether a merger happens at all within the next 10 billion years. Within the next 5 billion years, the original inevitable collision timeline, that probability drops to 2%. More data was supposed to give us a clearer answer. It gave us the opposite. The more precisely we can measure this system, the wider the range of possible futures becomes. Dr. Sangmo Son, one of the authors of the original 2012 paper, responded publicly to the 2025 findings. He agreed with the methods. He was, however, skeptical of one aspect of the conclusion, specifically the mass estimates used in the 2025 simulations. Son and his colleagues had, in the 2012 analysis, used higher mass estimates for both the Milky Way and Andromeda. Higher masses mean stronger gravitational pull. Stronger pull means a more probable collision. The 2025 team used more conservative mass estimates, lower values that reflect the current consensus in the literature. And that choice, more than any single measurement, is what drives the probability revision. What we have, then, is not a simple case of one paper being right and another being wrong. We have two careful analyses, using overlapping data, arriving at different conclusions because they made different choices about how to treat the mass uncertainty. The lead author, Sawala, addressed this explicitly. It's somewhat ironic that, despite the addition of more precise Hubble data taken in recent years, we are now less certain about the outcome of a potential collision. That's because of the more complex analysis, and because we consider a more complete system. Let that land for a moment. More data, more precise instruments, more complete models. And the answer is, we are less certain than we were in 2012. This is how science actually works. The first approximation produces a clear answer. The more detailed approximation reveals the complexity that the first one papered over, and the more detailed answer is, in some ways, harder to live with, because it does not give us certainty. It gives us a probability distribution. It gives us a range of possible futures rather than a single predicted one. For the scientists working on this, that uncertainty is an invitation. For the public, it might feel like a step backward. But for the question this documentary is investigating, the question of how much we actually understood about the future of the galaxies we live in, it is, in fact, a significant and honest step forward, which brings us to the second data source. The independent finding that, when placed alongside the Milky Way Andromeda collision revision, produces a picture of the Andromeda system that our models do not have a satisfying explanation for. That second finding concerns the Andromeda Galaxy's satellite galaxies. 37 of them have been identified and cataloged. Their positions have been measured with the precision that modern astrometry makes possible. And what those positions show is something that the standard cosmological model, the framework that governs our understanding of how galaxies form and organize, predicts should happen in fewer than 3 out of every 1,000 comparable systems. The details are in Chapter 5. But the question that Chapter 4 has to answer first is the one that explains why the collision probability changed so dramatically, and why the answer to that question is, itself, a different kind of anomaly. The Large Magellanic Cloud. If you have seen photographs of the southern night sky from the right location, maybe the high desert in Chile or the dark outback in Australia, you may have seen it. A bright, irregular patch of light visible to the naked eye that looks like a detached piece of the Milky Way, which in a sense is exactly what it is. The Large Magellanic Cloud is a satellite galaxy of the Milky Way, orbiting our galaxy at a distance of roughly 160,000 light-years. It is not a small object. By the standards of dwarf galaxies, it is substantial. Its mass is estimated at somewhere between 10 and 20 billion solar masses. That's roughly 15% of the Milky Way's total mass. For most of the history of studying the Milky Way Andromeda system, the Large Magellanic Cloud, the LMC, was treated as a minor player, a satellite, something in the background. Its gravitational influence was noted, but not considered decisive for the large-scale trajectory between two giant spiral galaxies. The 2025 analysis showed that this assumption was wrong. Here is the mechanism. The LMC is not static. It is in orbit around the Milky Way, a relatively short orbital period of roughly 1.5 billion years. As it orbits, its gravitational pull acts on the Milky Way, creating a kind of recoil effect. The LMC pulls the Milky Way in the direction perpendicular to the Andromeda Milky Way orbital plane, effectively nudging our galaxy slightly sideways. When you model the Milky Way Andromeda system without this effect, the trajectory points toward direct collision. But, when you include it, when you account for the LMC's gravitational influence on the Milky Way's actual motion, the Milky Way's path diverges from a direct collision course by an amount that, at interstellar scales, is really quite significant. The 2025 team's co-author, Alice Deason, described it in concrete terms. The LMC's mass, while small relative to the Milky Way, is positioned in a way that its gravitational effect runs perpendicular to the Andromeda approach vector. It's not pulling the Milky Way away from Andromeda directly. Instead, it's pulling us off the plane. And that small deflection, propagated across billions of years of orbital mechanics, is enough to change the outcome in a significant fraction of simulations. Professor Frank put the numbers into context with a specific example. The LMC's mass is roughly 15% of the Milky Way's. That may sound small, but consider this. If you're trying to predict the path of a billiard ball across a table, and you've accounted for friction, table tilt, and spin, but you haven't accounted for a hand that's very slowly pulling the table's left side toward it, the cumulative effect on a long shot will be entirely different from what your model predicted. That is, roughly, what the LMC is doing to the Milky Way in its orbital approach to Andromeda. A galaxy 1/7 our mass is, right now, redirecting us at the cosmic scale. In the time it took you to watch this chapter, the LMC's gravitational influence has moved the Milky Way's center of mass roughly 1,000 kilometers off its previous trajectory. 1,000 kilometers in 8 minutes. Sustained. Across billions of years. The cumulative deflection is enough to change whether our galaxy merges with Andromeda or passes it at distance. The effect of Andromeda's satellite galaxy, the Triangulum Galaxy, M33, acts in the opposite direction. M33 pulls on Andromeda slightly, which increases M31's acceleration toward us. So the two satellite effects partly cancel each other out. But the LMC's influence on the Milky Way is stronger than M33's influence on Andromeda, and its direction is more perpendicular to the collision axis, which is why its net effect is to reduce rather than increase collision probability. There is something worth pausing on here. The 2025 analysis was the first time these four-body dynamics, Milky Way, Andromeda, LMC, and M33, were modeled together with full uncertainty accounting. The reason this had not been done before was not scientific negligence. It was data limitation. The precision measurements of the LMC's orbit, mass, and gravitational influence on the Milky Way were not fully available until the Gaia mission provided them. So, Gaia changed what is measurable, and, well, what it made measurable changed the model. What the model revealed was that a factor contributing roughly 15% of the system's total mass had been, in practical terms, invisible to the prior calculation. Now here is the implication that has not yet been fully explored in the public coverage of this story. The LMC was hiding in plain sight, a galaxy visible to the naked eye from the southern hemisphere, one of the most studied objects in southern astronomy. And it was not in the model that predicted our galaxy's fate. The question that raises is not about the Large Magellanic Cloud specifically. The question is, what else might be missing from models that we trust with equal confidence? Not conspiracy, not negligence. Simple incompleteness, the kind that exists at the frontier of any measurement, where the precision of available instruments defines the edge of what can be known. The model that predicted the fate of our galaxy was missing a variable that was visible to the naked eye. That is not a failure of science. It is, in fact, precisely how science works at its best. Building on the data that exists, refining the model as better data becomes available, and remaining open to revision when the revised data demands it. But it is worth sitting with. The most confident prediction in modern galactic astronomy, a prediction that survived a decade of scrutiny, that was used as the foundation for dozens of follow-up studies, that was taught as settled science, was based on a model that could not yet account for the full dynamics of the system it was describing. Dr. Sawala said something in the announcement that deserves to be quoted directly. The only way to get to a new prediction about the eventual fate of our galaxies is to look at the data more carefully and include the most accurate and precise measurements. That is the scientific method working as intended. The data improved. The model was updated. The answer changed. What Chapter 5 examines is a finding that does not yet have an update. A finding published in the same journal in the same year concerning the same galaxy that the scientific community has not yet found a satisfying way to explain. And that finding, when placed alongside what we have just examined, produces a picture of the Andromeda system that our current cosmological models cannot yet account for. We've now looked at two independent layers of the same story. The 2025 collision revision, driven by better data and more complete modeling. And the mechanism behind that revision, a satellite galaxy whose influence had not been fully captured. Both findings point to the same underlying truth. Our models of the Andromeda system were missing something real. Something that was there all along, waiting for instruments precise enough to detect it. Everything examined in the last 35 minutes becomes the foundation for what Chapter 5 examines. Not what the collision data shows, not what the LMC's orbit tells us, but what the distribution of Andromeda's own satellite galaxies reveals about the state of our deepest cosmological models. The data in the next chapter is the reason this documentary exists. In April 2025, 2 months before the Sawala collision paper, a separate team at the Leibniz Institute for Astrophysics Potsdam published a study in the same journal, Nature Astronomy. The lead author was Koski Jamie Kanehisa, a PhD student at the institute. The paper's title was equally measured, equally scientific. Andromeda's asymmetric satellite system as a challenge to cold, dark matter cosmology. That subtitle, A Challenge to Cold, Dark Matter Cosmology, is significant enough to require some framing before the data is presented. Cold, dark matter cosmology, abbreviated LCDM, is not a fringe theory. It is the standard model of cosmology. It is the framework within which virtually all of modern astronomy operates. It describes how the universe formed, how galaxies evolved, how dark matter structured the cosmic web, and how satellite galaxy systems around large host galaxies are expected to behave. It is, in the language of physics, a paradigm. When a peer-reviewed paper in a major journal describes a specific observation as a challenge to that paradigm, it is not using that word loosely. Here is what the Kanehisa team found. The Andromeda Galaxy, like the Milky Way, is surrounded by a population of smaller dwarf galaxies, satellite galaxies in orbit around the larger host. As of the time of the study, 37 such satellite galaxies had been identified around Andromeda, catalogued, and had their distances measured with sufficient precision for spatial analysis. The standard cosmological model, LCDM, makes a specific prediction about how those 37 satellites should be distributed around Andromeda. The prediction comes from the theory of how galaxy formation works. Under LCDM, large galaxies form through a hierarchical process. Smaller structures merge chaotically over billions of years to build larger ones. The remnants of that process, the satellite galaxies that did not fully merge, should be scattered around the host galaxy in a roughly random, near-spherical distribution. Some clustering is expected. A modest degree of asymmetry is normal, but the overall pattern should be close to isotropic, distributed in roughly all directions, with no strong preference for any particular side. That is what the model predicts. Here is what the data shows. Of the 37 known satellite galaxies of Andromeda, 36 of them, all but one, are located on the same side of the galaxy. Not approximately the same side, not roughly half and half with a slight lean. 36 out of 37, concentrated within a 107-degree arc of Andromeda's surrounding space. An arc that, importantly, points directly toward the Milky Way. In cosmological simulations, a configuration this asymmetric occurs in fewer than 3 out of every 1,000 comparable systems. The Kanehisa team was explicit about what this means statistically. They ran their analysis against 2 of the most sophisticated cosmological simulation suites currently available, Illustrious TNG and Apostle. They examined hundreds of Andromeda analog galaxies in those simulations. In fewer than 0.3% of cases, fewer than 3 in 1,000, did any simulated system show a satellite distribution even approaching the asymmetry observed in the real Andromeda. None of them matched it exactly, not one. Dr. Marcel Pawlowski of the Leibniz Institute, senior author on the study, put the rarity in specific terms. We have to look at more than 300 simulated systems to find just one that is similarly extreme in its asymmetry as observed. I want to be honest about something here. In preparing this documentary, I expected one anomaly, the collision revision. There were 2. And they do not point in opposite directions, they point in the same direction. Both are evidence that the Andromeda system, as it actually exists, is behaving in ways that the models we use to understand galaxy evolution do not fully predict. The satellite asymmetry is not new as an observation. Astronomers had noticed it before. What the Kanehisa paper established for the first time, with statistical rigor and the most precise distance measurements yet compiled, was exactly how anomalous it is relative to model expectations. Previous analyses had left open the possibility that it fell within normal cosmic variance. The 2025 paper closed that possibility. At 0.3% probability, the Andromeda satellite distribution is not within normal variance. It is an outlier. And there is a second layer to the satellite anomaly that makes it stranger still. Of those 37 satellite galaxies, roughly half of them, approximately 15, are not just concentrated on one side of Andromeda. They are organized into a thin, flat plane. A disk-like structure in which the satellite galaxies appear to co-orbit in the same plane of motion, rotating together in a coherent pattern. This is sometimes called the plane of satellites. A thin plane of co-rotating satellite galaxies is already unusual under LCDM. The chaotic merger process that builds large galaxies is not expected to leave behind satellites organized in flat planes. Random accretion produces random orbits. But it had been possible to argue, when this plane of satellites was first noted in Andromeda, that it might be a coincidental alignment, an artifact of incomplete measurements that would smooth out as more satellites were discovered. The Kanehisa paper's use of consistent, high-precision distance measurements for all 37 satellites, rather than the mixed method estimates that had been used in earlier catalogs, eliminated that possibility. The plane is real, and the asymmetry is real, and both are present simultaneously in the same galaxy. In Chapter 2, we noted briefly, without explanation, that Andromeda's satellite distribution was described in the literature as unusual. That was the planted thread. Here is where it resolves. The Kanehisa team examined whether Andromeda's position relative to the Milky Way might explain the asymmetry. Whether the gravitational influence of our galaxy might be pulling Andromeda's satellites toward us, producing the observed one-sided clustering. This is a reasonable hypothesis, and the team addressed it directly. Their conclusion: the gravitational forces between the Milky Way and Andromeda are not strong enough over the relevant timescales to account for the degree of asymmetry observed. The effect exists, but it is too small by orders of magnitude to explain 36 out of 37 satellites being on the same side. So what does explain it? The honest answer, as of this recording, is that the scientific community does not know. The paper's authors offered several possibilities. A past major merger in Andromeda's history, a unique accretion pattern, some aspect of the local cosmic environment not yet captured by current simulations. But none of these explanations has been confirmed. None fully accounts for the observed configuration. And this is where the two anomalies, examined together, become something that requires more than two separate explanations. The 2025 collision paper showed that the Andromeda system was missing a key variable, the LMC's gravitational influence, that the prior models had not adequately incorporated. The satellite paper showed that Andromeda's satellite galaxy distribution is a 0.3% outlier in LCDM simulations. Both findings were published in Nature Astronomy within months of each other. Both concern the same galaxy. Both reveal that the Andromeda system, the galaxy we have studied longer, in more detail and from closer range than any other large galaxy in the universe, behaves in ways our best current models do not fully predict. The most studied galaxy outside our own is, according to two independent 2025 analyses, an outlier in the very cosmological model we use to understand it. And as of this recording, neither anomaly has a complete explanation. Either our models of galaxy formation and evolution are missing something fundamental about how satellite systems form and organize, or the Andromeda system is, for reasons we do not yet understand, genuinely unusual. Both possibilities have significant implications for cosmology. Both require explanation, and neither has received one. The question is no longer simply when the Milky Way and Andromeda will collide. The question is why the system that contains both of them looks the way it does, and what that appearance reveals about the limits of the models we have built to understand it. There is a discipline required in a documentary investigation like this one. It involves being as precise about what the evidence establishes as you are about what it reveals. An honest accounting of both is more valuable than a summary that blurs one into the other. So let's do that. Let's lay out, as specifically as possible, what the 2025 data actually confirms, and what it does not. What is confirmed? The Andromeda Galaxy is moving toward the Milky Way. That has not changed. The blue shift measurement, first made in 1912, has been verified and refined multiple times across a century. Andromeda is approaching at roughly 110 kilometers per second along the radial axis. That part of the physics is solid. What has changed is our understanding of the full trajectory. The 2025 Sawala analysis, using data from both Hubble and Gaia, incorporating the gravitational dynamics of the four most massive local group members, and running 100,000 simulations across the full range of measurement uncertainties, this analysis established, with the most complete methodology yet applied to the question, that the probability of a direct collision within the next 5 billion years is approximately 2%. The probability of any merger within the next 10 billion years is approximately 50%. Those numbers are the current state of the science. They are published in a peer-reviewed journal. They were produced by a rigorous, transparent methodology. They do not mean the collision is off. They mean the question is genuinely open in a way it was not believed to be 12 months ago. What is also confirmed, the satellite galaxy distribution of Andromeda is a genuine statistical outlier in LCDM simulations. 36 out of 37 known satellite galaxies positioned on one side of the host galaxy, concentrated in a 107-degree arc pointed toward the Milky Way. This configuration occurs in fewer than 0.3% of comparable simulated systems. The plane of co-orbiting satellites that roughly half of them appear to occupy is an additional anomaly, compounding the statistical improbability. Both of these findings are published in the same journal, by a separate team, with a separate methodology, examining a different dataset from the collision paper. Two independent anomalies, one galaxy. We built the most accurate simulation of the local group ever constructed. It told us we don't know what happens next. Now let's be equally precise about what has not been established. The satellite asymmetry has not been explained. The paper's authors are explicit. Several possible explanations exist. None has been confirmed, and the question of whether Andromeda's configuration is uniquely anomalous or represents a broader pattern in galaxy formation that simulations are missing, that question requires further observation and analysis that has not yet been completed. The upcoming Euclid Space Telescope survey is expected to provide data on galaxy systems at distances that will allow astronomers to search for similarly asymmetric configurations elsewhere in the universe. That data may reveal that Andromeda is a genuine outlier, a rare configuration produced by some specific feature of its history. Or it may reveal that the asymmetry is more common than simulations predict, which would indicate a systematic gap in the models. As of this recording, we do not know which of those possibilities is correct. The collision question has a clearer near-term resolution path. Dr. Sawala and his team noted that Gaia is scheduled to release additional astrometric data in the summer of 2026. That data will include more precise measurements of Andromeda's transverse velocity, the specific measurement that drives the uncertainty in the collision probability. When those measurements arrive, they may narrow the uncertainty range significantly and produce a revised probability estimate. But there is something worth noting about that expected resolution. Even if the 2026 Gaia data narrows the uncertainty, even if it pushes the collision probability meaningfully upward or downward, it will not change what the 2025 analysis revealed. It will not undo the demonstration that the prior model was missing the LMC's contribution. It will not erase the fact that the certainty expressed in 2012 was certainty built on an incomplete picture. There is a version of this story that ends with reassurance. The scientists found the error. They corrected it. The next data release will give us the real answer. That version is not wrong exactly, but it misses something. The real finding of 2025 is not that the collision is 50-50 instead of certain. The real finding is that the tools we now have are finally precise enough to reveal the complexity that was always there, and that the complexity, when revealed, shows a system that we did not fully understand even when we believed we did. Every map of the cosmos is a map of what we could see at the moment we drew it. The 2012 map was drawn with the best instruments available. It was drawn by rigorous scientists following careful methods. It was, by the standards of what was measurable in 2012, a good map. But the territory was more complex than the map could show. And it took instruments that did not yet exist, Gaia's full astrometric catalog, the computational power to run 100,000 simulations simultaneously, to begin to see what the territory actually contains. We are, as far as we know, the only species in this part of the universe trying to map the future of the galaxies. The fact that our maps keep needing to be redrawn is not evidence that the effort is failing. It is evidence that the territory is genuinely complex, and that we are genuinely getting better at seeing it. If you've been sitting with this investigation for the last 46 minutes and feeling the weight of what it means to have the most basic question about our galaxy's future genuinely reopened, that's the appropriate response. The scientists working on this question feel the same weight. The lead authors of both 2025 papers have been careful to emphasize that their findings are not conclusions. They are the current best picture, a picture that better data arriving in months will refine further. That is how it should work. We open this documentary with a question built on a century of accumulating certainty. The Milky Way and Andromeda were going to collide. The timeline was calculated. The outcome was visualized. The certainty for a decade after 2012 felt permanent. An hour later, that question is larger, not smaller. The collision is no longer certain. The galaxy we are headed toward is a cosmological outlier in ways we cannot yet explain. And the model we use to make the prediction, the standard framework of galaxy formation and evolution, is being pressed from two independent directions simultaneously to account for a system it did not predict. The next Gaia data release is scheduled for 2026. When it arrives, it will provide the most precise measurements yet of Andromeda's transverse motion. Everything we have examined today will either be confirmed in its current form, refined toward greater precision, or, in some respects, overturned again. That is the nature of science at its frontier. The universe does not hold its shape to fit the models we've built to describe it. There is a question this documentary has circled but not yet fully stated. It is the one that the satellite Anomaly raises, not about the Andromeda system specifically, but about what the Andromeda system represents. If the most studied large galaxy outside our own, a galaxy visible to the naked eye, examined by every major space telescope in operation, is a 0.3% outlier in our cosmological models, what does that say about the models? Not about whether they are wrong, but about where they are incomplete. That question has no answer yet. The Euclid telescope's upcoming wide-field survey may begin to answer it. The 2026 Gaia release will refine part of it. But the core of the question, why Andromeda's satellite system looks the way it does, remains genuinely open. And given how long the anomaly has been building without explanation, there is no reason to expect the answer to be simple. The universe has been doing extraordinary things for 13 billion years without asking for our understanding. This investigation is the record of one moment in the ongoing effort to catch up. When we started this documentary, the question was about a collision, a specific event, The Milky Way and Andromeda collision, that had been described as inevitable, calculated to within a margin of 100 million years, visualized in NASA simulations, taught in university courses, and accepted by the broad scientific community as one of the few settled facts about our galaxy's future. We now have a clearer picture of the data. The certainty is gone, replaced by a probability distribution that puts the original inevitable collision at 2% and the total merger probability over the next 10 billion years at roughly 50%. We understand why, not because the 2012 science was wrong, but because it was built on a model that could not yet account for the full dynamics of the system. The Large Magellanic Cloud was always there. Its gravitational influence was always real. The instruments to measure it precisely enough to include it in the model had not yet done so. And we have a second, stranger finding that emerged alongside the first. The Andromeda Galaxy, the single most studied large galaxy outside our own, is an outlier in the standard cosmological model in a way that 3 decades of simulations have not been able to reproduce. Its satellite galaxies cluster on one side in a configuration that the models predict should occur in fewer than 3 out of every 1,000 comparable systems. None of the simulated systems match the observed configuration exactly. These two findings are not the same kind of finding. The collision revision is a measurement refinement, a case of better data producing a better model, a case of science working correctly. The satellite anomaly is something different. It is a case where the data and the model have been in tension for over a decade, where the tension has grown more pronounced with every improvement in measurement precision, and where the scientific community currently has no confirmed explanation. The honest answer to the question this documentary started with, will the Milky Way and Andromeda collision happen? Is that we don't know. The more precise answer is that the question itself turns out to be more complex than the phrasing implied. We were asking about a collision. The data is telling us that the entire system, the trajectory, the satellite dynamics, the relationship between Andromeda and our cosmological models is more interesting and less well understood than the question assumed. The most unsettling part of this story is not the specific numbers, not the 2% and the 50%, not the 0.3% satellite anomaly. The most unsettling part is the pattern. Twice in the same year, from 2 independent teams examining the same galaxy from 2 independent directions, the Andromeda system revealed that our models were missing something. Both findings were published in the most rigorous available journals. Both were produced by serious scientists following careful methods. Both resulted in the same conclusion. The Andromeda system, as it actually exists, does not fully fit the framework we built to describe it. What makes this significant is not that the models are wrong. Models are always provisional. What makes it significant is that the specific object where the gaps appear, the Andromeda Galaxy, the nearest large spiral, the galaxy we have been able to study in more detail than any other outside our own, is the one place where those gaps should have been found and corrected first. If the most familiar galaxy in the universe is a 0.3% cosmological outlier, the question that follows is not just about Andromeda. It is about what else might be missing from the frameworks we use to understand the cosmos. Frameworks built on instruments that, until recently, could not measure what they were trying to describe with sufficient precision. The Gaia telescope, when it releases its next dataset in 2026, will give us better measurements of Andromeda's motion. The Euclid telescope, beginning its wide-field survey, will give us data on satellite galaxy distributions across thousands of galaxy systems at greater distances. Both will refine the picture. Neither will answer the deepest version of the question, because the deepest version is this. We are looking at a galaxy 2.5 million light-years away, a distance so vast that the light reaching us tonight left Andromeda before the first stone tools were made on Earth. And we are finding that it does not behave the way the best models we have ever built said it should. Not because the models were carelessly built, because the universe is more intricate than the models. That is not a reason for despair. It is the condition that makes science possible. The persistent gap between what we understand and what exists, the gap that instruments are built to close, and that every closing reveals to be deeper than it appeared. If this kind of deep investigation is what you come here for, the subscribe button means you'll be here for the next one. The Milky Way and Andromeda may or may not collide. The question, the real question, is not the collision. It is what the answer to that question says about how much of the universe we are still learning to see. Anomaly.